Today I am going to explain about another configuration which is called common collector configuration. In previous lecture we studied about common base configuration and common emitter configuration. Now we will see that common collector configuration. First we will see what is the connection for common collector configuration. The transistor which is connected in any network connected with base terminal is input and emitter terminal is output terminal and the collector terminal is common terminal. When we take in this common collector configuration, collector is connected to common for both input and output circuits. We have seen that four variables, among four variables, two from input side and two from output side, which are called input current and input voltage, and output current and output voltage. So this is the circuit diagram which gives the collector terminal is our common for both input and output. Actually here it is, output is taken at a emitter terminal. The input is given between base and collector terminal by providing battery. And output voltage, for example, VE is provided between emitter and with respect to collector terminal. And if it is required, we are providing proper resistors RP and RC. Providing proper biasings VPP and VE and RB and RC will get so a faithful common collector configuration. In this common collector configuration, first we will see the behavior of the common collector configuration can be explained from the two characteristics which are called input and output characteristics. Before going to measure the characteristics, input and output characteristics, now we come to know how to measure the voltage and currents at input side and output side in common collector configuration. We require measure the input current and input voltage, measure the output current and output voltage. How to measure this? All the four parameters. The emitter to collector voltage. The emitter to collector voltage between emitter terminal and ground terminal or common terminal, collector terminal is measured, can be measured by changing the position of the potentiometer R2. By changing the potentiometer R2. While base to collector voltage VBC input side, base to collector voltage can be varied or measured by changing the position of the potentiometer R1. If you use the potentiometer at a battery input side and a potentiometer at output side, by changing the potentiometer, we can be varied the collector to emitter voltage and base to collector voltage. And the DC ammeter, milliammeter and DC voltmeters are connected in the base and the collector circuit of the transistor to measure the voltage and to measure the voltage using the voltmeter, current using current ammeters. We have IB current can be measured the micro ampere micro ammeter. We can place the micro ammeter here and we can place the voltmeter here. We can place the voltmeter here between emitter to collector and we can place milliammeter in this emitter to collector between emitter terminal to supply. These two ammeters and two voltmeters. Remember, when we use ammeter between base terminal to base terminal to the base, we must use the micro ammeter. This is the simple connection of the common collector configuration. Input battery, input junction must be forward bias, so N is connected to minus and plus. Output must be reverse bias, P is connected to reverse bias, forward bias, reverse bias. When it is forward bias, due to base terminal is forward bias, all the majority charge carriers coming from P side to N or emitter to base can be represented by big arrow. And whenever it is base, the recombination takes place in the base is very less, then the current flow in the base or this one is very less, because of that base region is very thin and recombination in the base region is very less. So that what the maximum current coming from emitter or charge carriers coming from emitter reach to collector. This can be represented with this big arrow. And similarly, NPN transistor, electrons from emitter reach to base and reach to collector, then opposite, the current direction is opposite. Okay, the small current flow through base region is represented by small arrow. The symbol which are used in this common collector, so collector terminal is common and emitter terminal is output and base terminal is input. This is the symbol representation. So when it is arrow towards to the device or base, this can be represented with the PNP transistor. And when the arrow outside from the base terminal, and this can be represented with the NPN transistor. So we can use these two symbols while design or while connecting the transistor in common collector configuration. So most of the times we prefer symbols in the place of transistor. Now, steps to measure input characteristics. By measuring input characteristics, and we will see what is the purpose of input characteristics and what is the important parameter may need to be calculated in this input characteristics. So this is the same procedure which we had seen in the common base and common emitter configuration. Here also common collector also. In this common collector, when we see this is the symbol, collector is ground, input is base, emitter is output. Adjust emitter to collector voltage, output voltage. Keep output voltage constant. Output voltage means voltage between emitter terminal and collector terminal. This voltage fixed at certain voltage, fixed to certain voltage. Let us say 2 volts. Adjust output voltage, output battery. Keep emitter to collector voltage to some positive voltage. Keep some positive voltage fixed. Coming to the input side, by increasing the base to collector, base to collector VBC, base to collector voltage in small suitable steps, and record the corresponding current flow in the base current, and base to collector voltage. Base to collector voltage. It is very simple. Keep the output voltage. Keep this output voltage constant to some voltage like 2 volts. Come to the input side, varying the base bias voltage, and note down the base current and base to collector voltage. When we have base current, when we have base to collector voltage, and then plot the graph between base current and base to collector voltage. So when we plot the graph, we will achieve a input characteristic. This is the input characteristic. So the green color lines represents the input characteristics of common collector configuration. So this is one graph for VCE output voltage fixed to 2 volts. This is another graph, VCE is equal to 4 volts. Now, to obtain the first graph, keep output voltage constant VCE is equal to 2 volts. Varying the input base bias voltage and note down the voltage across base to collector and current flowing through the base terminal input. It is an input characteristic. It is a graph between input current and input voltage. So by changing the input voltage by varying the potentiometer and note down the base current and collector to base voltage or base to collector voltage. So by keeping output voltage constant, I am changing the collector to voltage between base and collector. So we keep on gradually when we slowly changing the base to collector voltage 0.1, 0.2, 0.3, 0.4. Likewise, what happened in the graph? How to change the graph? If in order to understand this slope of this graph, we can take mathematical equation for this one. We can take the mathematical equation for this the voltage. So for example, this is the emitter terminal, this is the collector terminal. The potential between emitter with respect to ground or collector terminal is nothing but sum of emitter terminal to the base terminal and base terminal to the collector terminal. This can be mathematically represented with emitter VCE is equal to the voltage from emitter point to ground is equal to emitter to base plus base to collector. So this can be used here to understand this graph. So what is the equation? The voltage from emitter to ground is equal to VEC is equal to VEB or VBE plus VBC. Now, when we take the VEB or VBE is equal to VEC minus VBC. Okay. And according to this procedure, keep output voltage constant. In this case, output voltage is equal to 2 volts. So it is 2 volts. When it is 2 volts, now according to procedure, keep output voltage constant and changing the collector to base voltage or base to collector voltage. The changing the base to collector voltage start from 0. When it is put 0 here, 2 minus 0 is equal to, and 2 minus 0.1 is equal to 1.9, minus 0.2, minus 0.3, and so on. When we keep on increasing collector to base voltage or base to collector voltage by keep constant of VEC, then resultant VB is gets reduced. When this value is reduced to 1.9 and so on, when it is changing from 2 to 1.9, 1.8, 1.7, likewise 1.7 and 0.5 and 0. So goes on increasing the base to collector voltage, goes on decreasing the base to emitter voltage. We have well-known parameter of VB is nothing but it is a base to emitter voltage input junction of the transistor, whether it is any configuration, any type of configuration. So emitter base junction always must be forward bias. So when the base to emitter voltage changing, the input current changes. So when input current changes by changing the base to emitter voltage. So this when base to emitter voltage changing from 2 volts, 1.9, 1.8, 1.5, 1.2, 1, 0.9, 0.7, 0.50. So the current decreases. The decreased current can be represented by a negative slope. Here it is. So by keeping VC is equal 0 is equal to, immediately the what is the VBE for our 0, VBC 0. When VBC 0, VEC is 2, VBC 0, VBE is equal to, its corresponding base current is nothing but maximum current. This one is the maximum current. When this VBC goes on increasing, that VBE goes on decreases, that decreases, VBE decreases means indirectly base current decreases. Base current decreases. When it is reached to base to emitter voltage reached to less than cut-in voltage, automatically current flow in the input junction is stopped. It has stopped. So because it belows the cut-in voltage, nothing but a cut-off region, then current flow in the base region gets 0. When it is 0 means is less than cut-in voltage, like 0.7, less than 0.7, 0.5, 0.4, 0.2 and 0. So the slope, negative slope will occur in this case. So the direction for this slope can be represented by this one. It is a starting point when VC is set to 0 and VBC 0. So this is 0 point and moving in this direction, and keep VC 0, VC 2 minus 0. This is the maximum current due to VB is equal to volts. When it is increasing the VBC and decreasing the VBE and current decreasing IB in this direction, reach to 0 current when VBE is less than cut-in voltage. Similarly, keep this VBC, VC is some 4 volts. Keep this VBE is equal to VEC minus VBC. So keep, according to procedure, keep output voltage constant to some 4 and changing the input voltage from 0 and observe the input voltage and input current. By changing the input voltage and observe the input current. By changing the input voltage, VBC 0, VBC 0.2, 0.64, 0.6, like 0.8, 1, like 1 point, like 2, like 3, like 3.5. So we'll get resultant voltage is for VBE voltage 3.8 and 3.6, 3.2, 3, here it is 2, here it is 1, here it is 0.5. So by increasing collector base to collector voltage, decreasing emitter to base junction voltage, base voltage. When base voltage decreases, which represents base current decrease. So if you reach this point, it is 0.5 nothing but less than cut-in voltage. Base to emitter junction must be forward bias. So when it reaches to less than cut-in voltage, automatically base current gets 0. So the direction for this graph is VC is equal to 4 and start from VBC 0. The maximum current is due to 4 volts. VB is equal to 4 volts. And then the current, IB current decreases until reach to 0 when it gets less than cut-in voltage. In this way, the slope, negative direction, negative slope in the input characteristic. So as voltage increases, the current decreases, so that we get the resistance will be very, very high. This is the input characteristics. From this input characteristics, we can measure, first one is input impedance or input resistance. Input resistance is nothing but, if you take this graph, I take one point like a change in voltage. So 3.8 to 3.6 corresponding current. So 3.8 to 3.6 nothing but 0.2 divided by corresponding current 2260 40 micro 10 power minus 6. So that 10 power minus 6, if it goes upside in the numerator, we will get will get 10 power positive 6. Almost we will get some kilo ohm or mega ohms. So nothing but input impedance is very high in the common collector configuration. And in this common collector configuration, we must operate it like this is the maximum base current and it will reach to minimum base current. You must operate it in this region. So input junction must be forward bias. We have another characteristics, output characteristics. From the output characteristics, we can get that output impedance and output current gain or voltage gain. So here the procedure to get output characteristics. How can we get output characteristics from the common collector configuration circuit diagram? From the general definition of configuration, output characteristics can be measured from output current and output voltage by keeping input current is constant. So first step, keep input current constant. Which one is the input current in common collector? Base is the input current. How can we set some constant to current in input base current? By changing the input voltage, base to collector or base voltage. So by adjusting the base voltage, keep input current, base current constant, let us say 10 microampere. Base is always measured in microampere. So adjust or keep base current IB to some positive current, let us take 10 microampere. Then come to output side, output collector region or emitter to collector region. In this case, change or increasing the emitter to collector voltage in a small suitable steps and record the two parameters. One is output current and output voltage. What is the output current? IE. And what is the output voltage? VEC. So by keeping input current is constant and come to output side and measure the output current and output voltage and plot the graph between IE and output current and output voltage. When we plot the graph, we can observe some important action in the common collector configuration. What is the behavior when we change that one, when we follow that procedure? So I am taking first graph, which is IB is equal to 10 microampere. Keep input current IB is equal to 10 microampere and increasing the output voltage to suitable steps. Okay, slowly increasing 1, 2, 3, 4 for positive direction, which increasing the VCE greater than 0 means it is reverse bias, collector to emitter or emitter to collector voltage. Increasing greater than 0 means it is reverse bias. IB is equal to 10 microampere, which means forward bias. When input junction is forward bias or input is forward bias, output is reverse bias. This region is called active region. So when if input is 10 microampere and changing the PEC from 0, then you will get the graph like this. So this graph, why this straight line? It maintains straight line. I will tell you later for this reason. So when greater than some VC is set, irrespective of the collector to emitter to collector voltage, it will still remain same or almost the same, which is equal to 1 milliampere. In the common collector configuration. So here, when we're changing the voltage, the slope you will get like this. So if you see slope, then you will get like this. So that slope means 1.1, 1.2, 1.3, 1.4, slowly varying. but up to this region, in this region only sharp increment in the current. Let us move to IB from 10 microampere to 20 microampere. If I am changing this curve to this curve and increasing the emitter to collector voltage, immediately the current slope, like output current, emitter current is like this. Okay. So still keep on moving 30 microampere, 40 microampere, 50 microampere, 60 microampere. You will get the slopes of the current direction is like this. You will get the slope for the common collector configuration. So this region is called active region. The entire this region, IB greater than 0, nothing but forward bias. VCE greater than point, VC some point, VC sat. This is reverse bias. So it is said to be in active region. Now let us see cutoff region. What is cutoff region? Let us take input is empty, or input IB is equal to 0 micro, means it is open circuit. Base terminal is open terminal. When IB is 0, which means a microampere current 0, then increasing the collector emitter to collector voltage and note down the emitter current. When by changing the emitter to collector voltage by keeping base terminal is open, but changing the voltage nothing but a reverse bias connection, changing emitter to collector. This reverse voltage increasing minority current flow between the emitter and collector. As I said, emitter is heavily doped and collector is moderately doped. So when we increasing the reverse voltage, a significant minority current flow or reverse saturation current flow between emitter and current. That minority current always some significant. So that's why we can show a dotted line having a small current flow in the graph. This dotted line which represents a significant minority current or cutoff current. So when compare with the common base configuration, input where input terminal or input terminal emitter is 0, when the entire emitter majority charge is coming from emitter terminal keep 0, that means reverse bias voltage between collector and base is very small. So that can be represented upon the x-axis. So it is negligible. So but here it's not negligible. It can show some significant current. So we can show a small graph of line upon the x-axis. This current is in this region is called cutoff region. Entire this region is called cutoff region. In this cutoff region, IB 0 means input is open terminal, means reverse bias, and VCE or VEC greater than some VC sat. This entire region is called reverse bias. So both reverse bias, then it is said to be cutoff region. Now coming to the saturation. In this saturation region, what happened in the saturation region? IB greater than 0, 10, 20, 30, 40, 50 is nothing but forward bias. 0 to 0.2. This point is called VC sat. VC saturation point. 0 to 0.2, very small region, little bit voltage. This 0 to 0.2, the increment in the emitter current is very sharp and very sharp increment, sudden increment in the emitter current. IB is equal to 10, varying the emitter to collector voltage from 0 to 0.1 suddenly increases. 0.22 suddenly increasing. So it reaches to maximum voltage and then slowly increasing. A small variation in this region greater than VC sat, large variation in the region below the VC sat. So this large increment due to this 0 to 0.2 in output is forward bias. So output forward bias, IB greater than 0, forward bias, both forward bias. This region is called saturation region. If you see some other graph, let us take 40. 40 microampere means forward bias. 0 to 0.2 is nothing but output forward bias. When change small variation in the 0.2 0.1 in the output, a large change in the current, which represents 4 milli, almost 4 milliampere. Sudden increment in from 0 milliampere to 4 milliampere, and when less than greater than VC is set and reach to 1 volt, 2 volt in the VC, and then this slowly increment 4.1, 4.2, 4.3, 4.4, like you slowly increment. This reason, whatever the sharp increment reason, this reason, this is the reason, this reason, the less than this reason is called saturation reason. So 0 to 0.2, 0 to 0.2 reason, 0 to 0.1 volt of VEC is nothing but saturation reason. So this saturation reason and cutoff reason is useful for transistor act as a switch, but whereas this reason, this red color reason, is active reason which is useful for amplifier. Now we will calculate the collector current. So here we can represent these three reasons: cutoff and active and saturation reason. IB0, VEC above 0.2 will take cutoff reason, reverse bias, IB0 reverse bias, and IB greater than 0 forward bias, VEC greater than 0.2 reverse bias, which is represented forward, reverse represents the active reason or active mode. IB less than 0, greater than 0 forward bias, and this 0 to 0.1 forward bias, both forward bias, it is in saturation mode or saturation region. Now we will calculate the collector current equation. As I said in previous lecture, IC is equal to, or IE is equal to, in this case emitter current is the output current, is equal to IE majority R plus IE minority. So majority current and minority current. Current flow due to big arrow. Current flow due to big arrow. For example, this big arrow represents majority current. This small arrow represents minority current. This small arrow, big arrow added together and reach to emitter. So the total emitter current is nothing but majority current and minority current. So here that emitter current can be calculated from basic formula in the common base configuration equation. So IC is equal to alpha IE plus IC B0. By taking this equation, if we substitute to get the common collector current, if you substitute IE is equal to IC plus IB, if you get IC plus IB, substitute in the equation IB plus IC, you will get IC is equal to alpha by 1 minus alpha IB plus 1 by 1 minus alpha IC B0, which is the representation of the collector current in common emitter configuration. Now replace this equation IC because we get output emitter current. So in order to get output emitter current, substitute IC is equal to total current IE minus IB. If you substitute in this way in the equation 1, how you can get by substituting IE is equal to IB plus IC to get entire equation in terms of input current and IC and IB in the CE configuration, input current and output current relation. Here in the common collector, what is common collector input and output current relation? Input is the IB, output is the, here it is there. this is collector, this is emitter, this is collector. So input is base, output is emitter current. So in order to get relation between IB and IE, replace this IC and put IC, put IE and IB. In order to get IE and IB, substitute IC is equal to emitter current minus base current in the IC. So substitute IE minus IB is equal to alpha IE in the equation 1, IC B0. And take the alpha IE terms left side, IE minus alpha IE is equal to IB plus IC B0. Then IE is equal to 1 by this, take the IE common. So we'll get 1 minus alpha. IE is equal to 1 by 1 minus alpha into IB plus 1 by 1 minus alpha IC B0, which is equal to 1 by 1 minus alpha, nothing but is a gamma in the alpha beta gamma relation. So IE is equal to gamma IB plus gamma into IC B0. So where gamma is the current gain in the common collector configuration. So this common collector configuration, base current, emitter current, gain gamma is equal to current gain in common collector is nothing but IE divided by IB, where output current IE is equal to gamma times of IB, current gain in IB, plus minority current 1 by 1 minus alpha, nothing but gamma times of IC B0, where IC B0 is called common base reverse saturation current. But when we replace in common collector configuration reverse saturation current, this entire equation can be represented with IEC0, emitter to collector current when base is open. So gamma IB plus IEC0 is the emitter current IE. Here, this is the collector current, collector configuration, common collector configuration, output equation. IE is equal to gamma IB, gamma IC B0. So when we see this comparison table between three configurations, by studying, before comparison, I would like to say how to measure the output impedance R0 is equal to change in output voltage VEC by change in output current IE. Okay, if you take the change in voltage 4 to 5, corresponding current 2.5 minus 4 divided by 2 minus some 2.2 something in milliampere current. So this way you will get a very less current flow, less resistance. So the output resistance is very less. So the small variation in the current, you will get like this 10 power minus 3 will get above, you will get output resistance is very less. So here, if you see these three configurations, the most important parameter we can calculate it like resistance, input and output, and current gain and voltage gain. What is the input resistance for common base configuration? Low input resistance and output resistance is very high. This quite opposite we observe in the common collector. High input impedance and low output impedance. So when we use common collector, then where the place require impedance matching or output impedance to match to the load. For example, loudspeaker in the amplifier, we can prefer common collector. The common collector is also called emitter follower. This can be useful for impedance matching or buffer circuit. So because of it has high input impedance and low output impedance. So when we drive to the low input, low impedance matching circuit, we can prefer common collector as a buffer circuit or this one. So because of this, it is a common collector is high input impedance and low output impedance. And when we see this a common emitter, both input and output having medium resistance when compared with the common base and common collector. So low to high region, high variation, it has medium resistance in the common emitter. Similarly, when we observe in the output resistance, common emitter is having medium output resistance. And voltage gain and current gain. So common base configuration having high voltage gain and current gain is very low, because here it is alpha. Alpha is equal to IE by IC. So IC and IE current are approximately equal, which is equal to 1. When alpha gain is equal to 1 means output by input is equal to 1 means output is equal to input. So gain is low. So current gain is very less, unity current gain. But voltage gain is maximum. Similarly, in common collector, voltage gain is low and the current gain is high, because here its relation is beta is equal to IC by IB. IC is equal to beta IB. So beta will get around 100 to 200. So gain is very large, current gain. But in a common emitter, both are voltage gain and current gains are having medium range. And when see this relation between input and output signals to amplifier. So whenever we are giving a signal to the common base configuration, you will get a same signal without any change in phase, zero phase. And here also zero phase. But a common emitter, you will get amplified signal like this, 180-degree phase shift observed in the common emitter configuration. So this is the way. What is the importance of configurations? Common base, common emitter, common collector. When any transistor connected in any network, electronic circuits, it must be one among the configuration CE, CB, CC. And when it is required, when we use common base, when we use common collector, when we use common emitter, based on these parameters, if you require high input impedance and low output impedance, like impedance matching, then prefer common collector. If you want low input impedance and high output impedance, prefer the common base at input side mostly. And common emitter is intermediate stage. Always prefer intermediate stage, like in the amplifier, to get amplified, okay, to improve the gain. To improve the gain, we can use multi-stage common emitter configurations amplifiers in the amplifier circuits. So in this way, we can prefer each configuration in each different situation. The purpose of these configurations have changes with the application. So these are the about the transistor configurations. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.